Well, a warm welcome back. How's it going, everybody? Get yourself ready with a notebook, grab a pencil or pen. Whatever you choose to write with is fine. This is math from the void. Math coming at you out of nowhere. And today we have a problem from the 1989 Calculus AB exam. This is problem 6 from that exam, apparently. And here we have a differential equation. So we're given a rate. We're also given an initial condition, and we're expected to go sort of backwards. Go ahead and give yourself about 12 minutes, maybe 15 if you need it. Attempt this problem. You can pause the video before I solve it for you. Do your best, and try to get it under time. And then when you're ready, come back, and you can see how it's done here. Alright, well, let's get started. Let's first analyze the problem. It's kind of wordy, this one. Oil's being pumped continuously from a certain oil well at a rate proportional to the amount of oil left in the well. So here they tell us that the rate, dy dt, is some multiplier k times y, which is like the current amount of oil that's left in the well. We're given this initial condition. Initially, there were 1 million gallons of oil in the well, and 6 years later, there were 500,000 gallons remaining. So, just want to mention this. If it's an exponential function, that means that 6 years is kind of like the half-life, so to speak. Yeah. You can actually get the k value quite fast from that, but we'll work through it more carefully. And maybe I'll give you the secret later. It will no longer be profitable to pump oil when there are fewer than 50,000 gallons. Maybe it's like not able to suck up enough oil at a certain rate anymore because it's too low or something. Who knows? You also have to pump all that oil up the well, so that takes some energy. Anyways, let's look at part A. Write an equation for y, the amount of oil remaining in the well at any time t. Now I said if this were an exponential, it is an exponential function. And we're going to solve the differential equation to prove that. But I also just want you to remember that when you take a derivative of e, in other words, its derivative, does it not just equal a multiple of itself? Usually the rule for e is that it's equal to itself, and then you use the chain rule if there's anything interesting in the exponent. Alright, so this is looking a lot and behaving a lot like e, but let's prove that for sure. So we want to solve this differential equation by getting all the t stuff on one side, which is kind of like getting all the x stuff on one side, and we want all the y stuff on the other side. We want the dt of dy to not be in the denominator though, so we're going to have to multiply both sides by dt. I probably don't have to explain it that thoroughly, I'm sure you're familiar with that. And we'll have k dt. So now when we are ready to integrate both sides, I know that doesn't look like an integral symbol, make it curly at the bottom, right? Then we're going to have ln, technically of absolute value of y. We know k is going to be negative because, well, the derivative should always be negative since we're always taking away oil from the tank. And this is going to be kt plus c. Alright, so we can sort of sniff out an exponential function here, right? That means that absolute value of y is going to be equal to e to the kt plus c, which based on the rules of exponents tells us this is going to be e to the c times e to the kt. So sometimes you'll see it in textbooks written as like some multiple c times e to the kt. Now that's a great general model, but we need to use the initial condition, which is that when t equals 0, So if t equals 0 and y equals 1,000,000, let's just go ahead and make sure that the y value is just in gallons. Y is the amount of oil left in the well. It doesn't really say units, which I'm surprised, but I'm assuming it's going to be gallons. And time is in years, we know that much. So in this instance, we have 1,000,000 equals, you might know that it's just c in front, but let's show that for sure. E to the 0 is just 1, so we have 1,000,000 for c. Now to find the k value, that's the interesting part. We know that at time t equals 6, that y equals 500,000. In other words, 1/2 of the original amount. So we could say that 500,000 is equal to 1,000,000, I know it's a very big number, e to the k. So that's just going to be 1/2. And therefore k is going to be, ln of 1/2, which is the same as negative ln of 2, just to let you know. So it is some negative value, just to let you know. Okay, so our model is going to be y equals 1,000,000 times e to the k, which is negative ln of 2, or we can just say ln of 1/2, times t. Okay? And so this is really the exact same thing as 1,000,000 times 1/2 to t, because e to the ln kind of cancels there, right? And this is our equation for how much oil is in the tank. Oh, did I forget the over 6? Thank you, person who's probably shouting at the screen. This is 6K. Yeah, actually, this is over 6. So let's make sure that we incorporate that. So this is going to be, 6K equals negative ln over 2. So this is going to be 1/2 over 6. Got it. So this is going to be t over 6. There we go. Just had to change our model a little bit. Just had to adjust it a tiny bit. Okay, now let's look at part B. Where is it? At what rate, so this is asking for dy dt again, is the amount of oil in the well decreasing when there are 600,000 gallons remaining? Well, for this we can simply use the dy dt they gave us, but now that we have k, we can say this is 1/6 ln of 1/2 times 600,000, which is just going to be 100,000 times ln of 1/2. I think that's the best that we can really write it. They wouldn't expect us to get a specific value, unless this were a calculator problem, in which case, go ahead and plug it into a calculator, if you're so curious. Negative 69,314.71. I'll put 3 decimal places, that's what they do often on the AP exam. And this is going to be in gallons per hour. So yeah, it's not happening immediately. It's taking some time. Great. Now let's look at part C. Part C says, in order to not lose money, at what time should oil no longer be pumped from the well? So we know that they don't make money after we get 50,000. So let's find out when this function is equal to 50,000. So 50,000 equals 1,000,000 times 1/2 to the t over 6. Right? What about right? Yep. So if we divide both sides, we're going to have a lot of zeros to cancel, but we're going to end up with 50 over 1,000, which is the same as 5 over 100, which is the same as 1 over 20, and that's going to be equal to 1 over 2 to the t over 6. So we can solve this with some basic pre-calculus skills. We can just take a logarithm of both sides. And so we can bring the power out in front, t over 6. And that'll just be ln of 1/20th over ln of 1/2. And then we're going to multiply both sides by 6 as well. Yeah, this as well we would not be expected to do by hand. There's no reason why they would expect us to do this by hand. But this is going to be approximately 25.9315. So I'm going to call this 25.932 hours. Notice that you would also be able to graph the function if this were on a calculator problem. You would simply be able to say that y equals 1,000,000 to the x over 6 power. That's looking about right, about 25.9315. So we can round that up to 25.932. And that gives us the amount of time until the level of oil is so low that it's no longer worth it to even pump it out of there. Okay. All right, so not too bad. It turns out it was a calculator problem after all, but part A didn't require much of a calculator. And I did mention I was going to share a little trick with you. So when you have this kind of a model, and we have a half-life model, we already know that the equation is going to be in the format A times 1/2 to the t over t 1/2, which is what we call the half-life amount of time. So 6 would be going there, and the a value is simply the initial amount, so 1,000,000. That could get you to the equation right away without technically integrating both sides, if you're really good with your pre-calculus. That being said, you'd have to make sure that you're carefully stating your argument along the way, otherwise they're not going to understand how you got to there. So if you say half-life model equation, and then you plug in the half-life, you say the half-life t 1/2 is 6 years, and the a value is the initial value. If you just do that, you will be able to get some full points for that. So just wanted to let you know there are many ways to go about this. As long as you're supporting your answer along the way, you should be fine. Okay, that's enough blab out of me. I'll see you guys next time in the vlog.